Okay, hello everybody, thanks for coming. I'm Adam Spires and this is Dirk Muller. We're OpenStack, SUSE OpenStack cloud engineers on the cloud team. We've been on the team since pretty much the beginning. And today we're going to talk to you about log files and how we can get smarter with machine learning. So we spend a lot of time on a daily basis staring at log files, figuring out what's happening inside the product, what things are going wrong. And we've spent so much time on that over the years that we've felt the need to come up with more and more efficient ways of looking at log files and doing troubleshooting and root cause analysis. So today we want to show you some concrete techniques that we've developed and are still developing, which hopefully you will potentially find that you can apply yourself in other contexts. So CI, continuous integration, is a critical part of our product, like so many other products and IT projects across the industry. It's really the beating heart of our product. We actually have something like 300 or more CI jobs by now. And you can see that this is just a little glimpse of some of the jobs that we run in our Jenkins. We actually have multiple Jenkins instances, and we have other lots of different CI set up. We have jobs for the different releases of our product. We have our product is highly configurable and flexible. You can make it, configure it in all kinds of different ways, and obviously we need to test as much of the supported configuration as we can, so that we can ensure that the product stays at the highest quality. And so it's really a mission-critical part of our development process. And when things go wrong with the CI, it can be very expensive, not just in terms of trying to figure out what went wrong and fixing it, but it can have a knock-on impact on our whole development workflow, because we have a complex development process that involves code review and merging, and we have a policy of not merging stuff if the CI that is running on those changes is broken. So if a CI job breaks for a reason unrelated to a code change that is currently being reviewed, then it blocks the merge of that change, which means that the developers working on that change are now in this blocked state where they can't proceed with their work, and it may not be their fault. The problem may have come from somewhere else. So it can be an expensive thing in terms of actually the cost of human resources as well. So we really want to make sure that we can fix CI as quickly as possible when it goes wrong. And that was from a product perspective, but a key part of our product is OpenStack. Of course, it's the main part of our product, SUSE OpenStack Cloud. It's even in the product name. And so the upstream OpenStack community product is the most significant part of our code base, and we work with the upstream community on that. And OpenStack itself has a huge number of CI jobs and a very sophisticated CI infrastructure of its own. And of course, we contribute along with the rest of the community towards maintaining that and developing it. And this is just a graph of one particular CI job in OpenStack, and you can see it's running on a regular basis, and things can fail unexpectedly. And this is actually coming from OpenStack Health, which is a very nice website that allows you to introspect all the different CI jobs within OpenStack. Here's another view showing you a small fraction of all the jobs, and then giving you some statistics about which jobs are healthy and which aren't. I'm not sure how easily you can see the background colors on there, but the first 3 rows are red because there's some failures occurring, and then the rest are kind of a pale green, or at least they are on this screen. So yeah, that's OpenStack Health, and actually the concrete software project that we're going to talk about and demo today emerged from the OpenStack community, from one of our colleagues in the community, and we liked what he was doing in the direction he was taking this in a goal to make debugging of OpenStack CI more efficient. So we jumped on board and started helping develop it and started using it for our own internal CI as well. So this is sort of a zoom out of about 2% of one of the OpenStack job logs for a particular OpenStack infrastructure job. So the full log is like 98% more than, well, yeah, it's like, yeah, 50 times bigger than what you can see there. Actually, is there anyone here who works on OpenStack upstream at all? No, okay. So do you think, like, just looking at that 2%, any ideas of where the error might be in that? This is a failing job. Well, it's not really a fair question because you can't even read it, let alone, and if you haven't looked at that before, then why would you know? But actually, if you've ever looked at Ansible job logs before, then you might sort of recognize the structure, because at the end of a long list of outputs, it runs through all the tasks, and then at the end it will print a summary of what happened, and it will give you a little sort of indication, and that's actually down here. So that, if we were able to read that, that would give you a hint of where to look for the error. And so what the general process looks like for, in many cases, for manually debugging, troubleshooting CI failures, is that usually there'll be one main log that shows you the kind of the high-level view of what was run, but then that will there will be lots of related artifacts, other job files from particular services and different things that ran in parallel and that got captured in different places, and they would be gathered at the end of the failing CI run. So typically what you would do is start with the kind of main log, scroll and scroll and scroll and scroll until you find what went wrong, and then once you found that, you will see that there's a reference to some other service or some other component in the CI run that went wrong, and then you would have to open up that separate artifact or that separate log file for that particular component and do some more scrolling within that to find out the details of why that component went wrong, and finally, hopefully you get to the root cause. So the main the most time-consuming element of this is really the scrolling and kind of wading through gigantic log files, which can often be very complex, and you don't always know what you're looking for, so you can't just do a Control F and search for a particular thing. So our first iteration, I guess, was about maybe 2 years ago. I thought, okay, surely we can do better than this. And I found this plugin to Jenkins called the log parser plugin. And what you can do is basically configure it and say, just look for lines in my log file, in my main log file, that match a certain pattern, and then mark that line as an error or a warning or maybe just an informational thing, and it will just highlight those. So the first iteration was just really naive, just look for anything that says warning or error or failure or fatal, stuff like that, or stack traces, and just tell the log parser plugin to just highlight those lines, basically, and at least then we don't have to scroll through tens, hundreds of thousands of lines manually to find where things go wrong. So when you set that up, then it's, rather than just having a plain log file, you get this nice little kind of navigation bar on the left-hand side, and here we can see it's found 4 lines matching the error regular expressions that we set up, 11 lines matching warning, and then 58 informational. And in the way I configured this was informational generally corresponds to the beginning of different high-level sections within the log file. So, you know, if you could kind of zoom out from the log file and see at the high level what are the main steps that are happening in there, there are certain lines in the log file that are kind of section headers, and the info thing is matching those. So then you can click on error, and it expands, and now you can see those 4 errors. So you can see the actual text of those lines, and then when you click on one of those, then it instantly jumps to that error, and you can see it highlighted in red within the log file. So then you can, you know, scroll up and down and see the context around that error and try and figure out, you know, is this the error that was the root cause of the thing I'm trying to debug, or maybe it was just some other red herring. So this instantly, you know, solves the scrolling problem to a certain extent, and that's quite nice. But it's pretty naive, as you might guess. You get false positives, the things that you get lines which mention the word fail or failure or failed or warning, but they're actually not things that we really need to worry about. So it might be just something as simple as an RPM that has the word error in it, or a grep command that is searching for the word failed because the CI is doing some of that itself automatically. So then we need to manually create this long list of regular expressions just to, you know, reduce the noise of what's being picked up. And this is a, you know, painful exercise, and it has to be done for every scenario, every context in which you're trying to streamline your CI troubleshooting process. So you would have to, you know, this one is for our internal CI, but the same process would have to be applied for the upstream OpenStack CI and so on. So really we want to do better, and the vision is to just have, you know, the computer do everything, right? So you just push a button and it runs the CI and then just instantly tells you what's wrong. Now, that's the vision. I'm not claiming that we've got there. Of course, you know, it's a work in progress, and machine learning in general is a field very much in progress. But that's, if we aim high, then hopefully we can get somewhere a bit closer to it. So the main topic of today's talk is this new tool called log classify, and I will hand over to Dirk, who is going to give an introduction to machine learning, and then we'll and some of the concepts that we apply, and then we will talk about the implementation, how it works, and we'll give a kind of demo of the tool actually in action. So,
thanks, Adam. So the field of AI is pretty large. In general, it describes anything that tries to mimic human intelligent behavior. Machine learning, more specifically, is referring to a subset of that field that is using statistical methods or algorithms that are based on statistical approaches to infer or get patterns out of large sets of data. Deep learning is recently more popular in the news, which is doing machine learning using artificial neural networks. And artificial neural networks are trying to somewhat reflect the way human or biological neurons are working, but only to some extent. So to explain visually why machine learning can be useful, I made a very quick example. So this is the English Wikipedia article about machine learning. Can you guess what it is about? So if you've seen word clouds before, it zooms the word depending on how often it is being used in the text. So just without any understanding of what the text is actually about, or what the structure is, or what the language is, we can see the topic of this text. So in general, this is the idea behind machine learning. So it is clever, but it's actually based on relatively simple algorithms that, based on large sets of data, can produce interesting results, and that's what we are looking for. So to apply this to CI log files, we had to do a little bit of thinking process, because the popular use cases around machine learning or AI in general are usually about video, images, text, or speech recognition, or any kind of audio processing. And when it is about text, then usually it is about like natural language text, or like trying to translate text from one language to another language, or by, for example, doing sentiment analysis, or trying to figure out if this text was written by someone who is happy or unhappy, or things like that. And this is not so useful when you talk about log files, right? And at the end of the day, we don't care about that kind of analysis. So for CI log files, we have to think a little bit outside the box and try to see how we can make that useful. In general, CI log files are very well structured, very regular structured. So every CI run more or less has the same structure, which is really good, because that means we don't have to use a lot of training data in order to understand the structure. Unfortunately, the individual log files are very quickly evolving. So in an ideal world, every new check-in or every change to the product will add a feature, or it will add a test case which is getting logged. So the log file will very rapidly change over time. And also, which is the bad thing, every log file has a lot of unique, very random noise. So for example, there are timestamps in there, there are passwords that are randomly generated on every run. So they're completely unique, and they're often logged for debugging purposes, but they are actually just a distraction from the real log file content that we are trying to analyze. So to give a little bit more overview about machine learning models, algorithms, you can categorize them into instance-based algorithms and generalizing variations. So the instance-based ones, they are basically in the learning phase storing the input in the model, more or less unmodified, which is why it's called instance-based. So the model is based on the instances of the testing data or the training data. And this has some advantages. So the main advantage is that you can very quickly update a model with more testing data, because you can just use the existing model, add another training set, and update it basically that way. You can also retroactively remove training data from the model, because it's literally somehow stored in the model, so you can just wipe out parts that you don't consider relevant anymore going forward. In contrast to that, in the generalizing algorithms, the model is basically reflecting some kind of generalization or abstraction from the input, from the training input, which means that you have to train on a lot more data than an instance-based model in order to infer a useful model. And you can also no longer untrain something that you have trained before. So the only way to untrain something is by throwing away the model and starting from scratch using like a modified testing or training set. All of those algorithms are affected by overfitting and underfitting, which is a common problem everyone has to face. So in this example, the algorithm was supposed to cluster between the red and the blue dots. And ideally, the clustering separation should look like something like the black line on this picture. And in the overfitting case, which is reflected by the green line, basically what we have done is the testing or the training set was too large. So we trained on too much data, and the model was overly fitting this training data. And this results in, for the training data to be very accurate in the result. But if you think about like a new data that hasn't been seen before, and which is the case that we're actually interested in, it's like applying the model that we've learned from previous training data on something new that you want to analyze, The green model will most likely perform worse because it's like overly specific. It's not general enough to fit on a similar but differently structured input data. And the opposite of that is the purple line. This is when the model is basically not able to reflect the complexity of the input. So either you had not enough input data, or the model was not able to actually properly capture the characteristics of the input. In general, machine learning algorithms can be either supervised or unsupervised. Unsupervised use cases are this clustering that I just explained. There are a couple of names on the slide. I'm not going to explain all of them. In the supervised case, the most typical example is classification. That's the part that we are going to look at further. And regression. So classification, basically that means someone has to do the due diligence, and in this example we are trying to classify pictures of fruits. So someone has to build up a training data set of some set of pictures and manually label them. So they has to go in, oh, okay, this is a banana, this is an apple, this is a strawberry, and so on, and manually assign labels. And then you have a training data set with labels. And by putting that into the algorithm, you can build a model that when you have enough inputs trained and properly labeled, you can apply on a picture that was not in the previous training set, and it will most likely infer from that the correct label. So that's the idea that we are trying to pursue. So when we try to apply that to the CI logfile case, the simplest algorithm that can be used is the nearest neighbor algorithm. And I'm going to explain that in a little bit more detail. So just to make sure that I'm not confusing you, so a build in the following slides means it's one log file of one particular CI run. And a baseline is basically a set of builds, so a number of CI runs that are from successful runs. And those are the ones that we keep aside as training data. And we use that to infer a model. And with that model, we will run it against a target. And the target is basically the CI run that has a failure, that has been failing, and where we want to learn more about what was the reason for the failure. To give you an analogy with pictures, heap of leaves, another heap of leaves. Do you see any difference? Who sees one difference? Raise your hand. Oh. Do you see two differences? Do you see three differences? Do you see four? Do you see five? Okay. So I guess you get the idea. So humans are really good at spotting one thing, but there are actually many differences in the picture. You just have to trust me on that one. And machines are better at extracting all the differences than humans are. And actually, the analogy here is that for CI log files, sometimes not the most obvious error is the one that leads you to the root cause, but maybe this small random thing on the side node that actually caused the chain of things to happen that will cause the actual failure that you see later. So in the tool log classify, we have to collect a set of baselines. This is basically the CI log file. So every green bar here is one line of text in there. And we have many of those log files. And we are transforming them into a representation that we use for the model. And I'm going to explain that transformation step in a little bit more detail. And this is basically the model, which is an instance-based model. So we are just more or less storing the transformed input training model. And oops. For evaluating a target, which is really a failed log file, we are doing the very same transformation that we did in the training phase and run it against the already pre-generated model in order to extract relevant set of anomalies. And from that, we are generating either a pure text-based or an HTML-based or an interactive report that can be analyzed further. So to give you an example how the transformation is working, so in this example, we have a raw text line that is from some syslog entry. And the first step that we are applying is tokenization. This basically means we are removing short words that are probably not relevant. So if you compare it, any word that has less than 3 characters is being removed. And we are also removing random strings that we think are not relevant for the result. So for example, in this case, we have replaced a date string that we have detected using a regular expression with the word date. And furthermore, the next trick that we are going to apply is that we are changing this tokenized string by applying a hash function on each word. And the trick for hashing is that it will predictably produce a number. So the same word will produce the same number. And hopefully we don't have a lot of collisions, so different words will produce different numbers. So basically we have a direct mapping from words to numbers, and we can use those numbers as an index into an array. So we are in this form, we are only storing whether in a particular line of log file this word occurred or it didn't occur. So if anywhere this particular word occurred, we are storing a 1 at that particular location in the vector. Otherwise, we are storing a 0. So particularly, we are ignoring a large part of the input because we are ignoring if a word is mentioned multiple times, and we are also ignoring whether the word, in which position of the line the word was mentioned. So whether it was at the beginning or at the end, we are ignoring that information. Other transformation that we are applying is like basically we are trying to remove any noise that we consider not relevant for the CI use case. So for example, UID strings which are recognizable, or IP addresses because they usually change between different runs, or words that have a specific length because we have seen in our occurrences that special lengths like SHA sums or MD5 sums are a word with particular character set and a particular length, and we're just replacing them with a fixed string, basically. And to give you an example, so this is how a log file that has been transformed looks like. So on the x-axis, we can see a line. So this is the first line, and the end of this is the last line of the log file. And over the left side, no, it's actually the other way around. We are seeing the entries on this vector that I described before. So if you look really closely, and maybe you've drank some whiskey last night or so, you can see some kind of structure in there, but it's like really difficult to see something. But you can see maybe that near the end, the structure of the input is slightly different than in the middle. So that's the main thing that we can see. But the nearest neighbor algorithm is actually performing on this very well. So in the example, we have one line in the target, so in the log file that we are actually interested in analyzing. And that this reflects or is represented by this vector. And the algorithm is looking for an entry in the baselines that is similar to that one. And it gives us not only whether this line is in there, but it also gives us the distance to this line. And we can, by accessing the distance, we can look at how relevant this particular line that we're analyzing is compared to the baseline. So in this example, we're looking at this log file entry, which has a unique character. So it has this string, variable is not defined. So immediately that raises our attention as a human because that looks like an error to an engineer, right? So something went bad here, and actually there was supposed to be a variable here, but instead somehow an error message went into this part of log message, which is called variable is not defined. And the nearest neighbor algorithm is actually exactly telling us that. So it can identify from the baselines that there is a vector that contains controller and ephemeral device, because that always occurs. But the 4 entries variable is not defined are nowhere to be found. So this gives a distance, because this is not part of the baseline. And the distance is relatively large, so it can be between 0 and 1. So with 0.9, it's basically a very large indication that this is an anomaly in the log file. So to summarize, the nearest neighbor algorithm performs a linear search in the baseline. So if you're a software engineer, you know linear searching is bad, because that means it has a impact on complexity. So when the baseline gets bigger, your search time becomes longer, and you need more memory for that. Also, unfiltered noise, so noise that is completely random, will actually confuse the algorithm. It will find matches where there are no matches, and vice versa. So we have to be careful with logs that contain too many completely random features, like strings that are unique for each run. So to give you an example, this is a baseline that has been trained on a variety of different inputs. So on the x-axis, we see the number of CI runs that we have been used as the baseline, and this is the size of the model that has been generated as the y-axis. So you can see that around about 10 baseline jobs, we have reached some kind of plateau, which is then slowly growing. So this slowly growing means there's additional instance-specific features that are getting learned over time, but most of the features have been learned within like 10 various variable jobs already. And then apparently, so this is an artifact like this hump over there is indicating that something has changed over time, and there were new features or a new functionality being added, so new features were able to be learned with more training data. And you can also see the lookup time is the same like I explained before. It's strictly linear. So the larger the model, the slower it becomes. Now I'm going to hand over to Adam again to give you more hands-on examples from log classify.
Yeah, thanks. Okay, so that was the principles behind this particular implementation. So now we're going to go into a bit of the detail on the implementation, and it's called log classify, and we use the code base uses a toolkit called scikit-learn, which is an open source machine learning sort of framework that can do lots of different things. And Dirk has actually been looking at using TensorFlow as an alternative approach to the current implementation, but that's very much still work in progress. It's based on Python 3, and the text extraction process that Dirk was just talking about is sort of modular in design, so you can switch out different approaches to text extraction. So there's definitely potential for trying different approaches to that in the future. But it does assume that this, a log line based thing now, just text split into lines. So yeah, scikit-learn is a very nice toolkit that has various libraries providing approaches to different types of machine learning. So you can see the sort of high-level bubbles there. It does regression, classification, clustering, dimensionality reduction, all these things that Dirk mentioned before, and it has a nice kind of cheat sheet workflow thing guiding you through, so that if you're not sure which algorithm that you want to use, then you can just sort of follow this cheat sheet and it will help you find the right algorithm. But yeah, the implementation in log classify, as mentioned, is the k nearest neighbors for now. And installation is pretty standard in a SUSE world. I mean, and also in the Python world in general. It's on PyPy, which is the standard Python module, online module repository. So you can install directly from there, or you can just do a zipper install, or any of the normal, the usual installation routes on OpenSUSE or SUSE Linux Enterprise. You will notice there that there's a reference to logReduce in the Python module name. So it used to be called logReduce, but it's now being renamed. Is that because there was a clash with something else? Yeah, there was another logReduce out there. So so there's a rename in progress to logclassify, but it's not yet reflected in the package names and the Python module names. So there's a command line interface that has various subcommands. So you can just do a simple run where you just do a logReduce diff and point it at, a couple of files, for example, or a couple of directories, or maybe several files as the baseline that it will train against, and then finally it will do a diff of that baseline against the final argument in the command line, as using that final argument as the target. Or you can split up the building the model phase and do that separately from that training phase separately from the comparison phase against the target. So the dir subcommand is basically doing dir train and then dir run all in one, but you can run them individually, which can be useful. In fact, I was in the preparation for the example that I will show shortly. I used dir train because building the model was actually quite an expensive thing that took quite a long time. So, but I wanted to, once I had the model built, I wanted to keep running it again against different targets, and then tweak the outputs and do some comparisons and so on. So that splitting it out allowed me to be more efficient and not have to continually repeat the same training over and over again. So you can also run it against CI logs. This is the job is the Zool integration, and you can also run it against a local journald on your system and just grab log lines directly from journald. And I think there's a slide on that actually later on. So Dirk has already explained this, but just to emphasize, so the baselines that we're training the model against are successful CI log runs, and then once we've built that model, then we point it at a failed CI run and do the comparison and find out what deviations or what anomalies in comparison to the baseline it can find. So if you run it as just a simple, a single baseline, the good.txt, and compare that against a bad.txt, then it's just pretty much acting like a kind of fuzzy or intelligent fuzzy diff, and it will output all the lines that in the bad.txt that exceed a distance threshold from any lines in the good.txt, and you can see the figure on the left-hand side, the 0.527 is the distance, and that's so 0 would be is no distance, so that's only for lines which are identical to those already in the model in good.txt. So typically, if you're running this, it will either, depending on how you specify the command line options, it's a bit like diff actually, where you can. How many people here have used diff, the command line thing? It's very popular, right? And you know how you can, well, there's not necessarily, we might have some, product managers here. I'm kidding, all our product managers know diff. So with diff, you can specify how much context you want to see either side of the lines which actually differ, and this actually has the same approach, so that you can control how much context you want to see before and after the lines that differ. And actually, I just the other day submitted a patch to this so that it actually uses even the same single letter options for controlling the amount of context that you get. So if you're familiar with diff and its context options, then this should feel very familiar. And then at the end, it tells you how many lines it basically hid, because this is lines in bad.txt, which it didn't display because it also found the same lines after the noise reduction and extraction in good.txt. So, you know, basically this is telling us, rather than, if this is a failed CI run in bad.txt, rather than having to read 35,000 lines to find something useful, we only have to read 712, which is obviously a pretty huge improvement. And in some of the examples I'll show in a bit, I think it goes even higher, up to like upwards of 99% reduction. So this is where the reduce part of the word, the name log reduce comes from, because it's, you know, hiding all the stuff that you shouldn't need to care about. And this is just a visual representation of the that noise reduction process. Now this is using a visualization technique called SVD, which basically takes a high dimensionality space and compresses it to 2D, just so that you can get a feel for, because obviously we can't look at things in, you know, 1,000 dimensions. So by compressing to 2 dimensions, you can look at something, and even though the exact positions in 2D don't mean anything concrete, it still gives you an idea of the shape and the size and relative sizes and so on. So what it's showing here is that the gray dots all correspond to vectors in the high dimensional space that have been directly extracted from the log lines. And then the red dots are the ones that you still get after you do the noise reduction that Dirk explained earlier, of all the things about removing IP addresses and date stamps and you know, words that are shorter than 3 characters and this kind of thing, so that you're only focusing on the things that you think have a significance in this context. So you can see it's yeah, so everything that is not red is considered noise, and it's, you know, it's not a precise science, so we don't have any guarantees that this is, like, you know, the optimal way of doing noise reduction, but it's something that could be experimented with, and empirical observations could be made about effectiveness as part of the development of this tool. So as I mentioned before, we can split the training phase away from the actual the run of the reduction. So in this case, we persist the model. We build the model and then persist it to this file called model.clf. CLF is just short for classify or classifier, and so that's built from, you know, all the, in this case, all the files in the baseline subdirectory. And you can see here it tells you that how long it took to process 8 logs. And then once you have that model, then you can run it on error.txt, and it will again tell you what the reduction was and how long it took to achieve that. So there's a question, you know, given that the training phase takes a while to run, depending on the size of the inputs, of, like, you know, how many megabytes or gigabytes or terabytes should we feed in to build the model to achieve reasonable results, given that that's going to take a while. And this is the result of some empirical research that shows the, like, as the number of baseline inputs goes up, you get diminishing returns. So yeah, 4 to 8 samples for the baseline seems to be a pretty good kind of starting point. And actually, I think the example that I'm about to show you was built on only 3, and it's already you know, achieving some useful things. So this is the example of running it against journal D, and you can specify date ranges to say when you want to operate over. And here's some more examples. You can see here that it's found this cron error is an unusual one. It's scoring 0.7. I think one is the highest score, so it's between the distance is calculated, ends up being between 0 and 1. Actually, is it just the Euclidean distance? Because the bit vectors are just, for each dimension, it's a 0 or a 1, so it's just calculating Euclidean distance over all the dimensions, which is why the distance is always between 0 and 1. Distance of 0, like I said before, means that we've seen this before. This is identical to something we've already seen. And in this case, I think this was on your hard disk, right? And so when Dirk was playing around with this, he found, oh, there must be a bug in logReduce because it's discovering that I have one uncorrectable sector on my hard disk, and this is clearly an error that I should be worried about. So must be a bug in the code that is causing it to say this is classified as a normal behavior rather than error. But then when he looked into it closer, he found that actually this uncorrectable sector had been around on his hard disk for actually longer than he like several months. So it had ended up being trained. The model had been trained to think, oh yeah, it's normal for hard disks to have uncorrectable sectors. So that is an important kind of warning that you should bear in mind if like the model is only good as what you train it with. So if you're not being careful about what you're feeding in and what you're saying is successful stuff, then you might run into problems because it might fail to detect stuff. And there's another example of killing the automount service, and then it spots that it's failed in a way that it hadn't seen before. This is running it on OpenStack log files, same kind of thing. Again, pretty big reduction, finding an unusual message. And Dirk has added support for support configs. Just in case anyone doesn't know what support config is, it's our method of collecting debug data from SUSE Linux Enterprise systems so that we can have all information about a system and don't have to go back to a customer or a partner and say, oh, can you just send us that other file because we were debugging your problem and we realized we didn't have a log file that we need. So, and then you can waste a lot of time just going backwards and forwards saying, oh yeah, and I need that log file and that one and that one. And so we just run support config, collect it all, and then we have all the information we need for proper diagnostics and troubleshooting. And that gets kind of zipped up into an archive like a tarball, and then when we're looking at it, we unpack it and do analysis on it, and the tool knows how to do that basically, and it knows how to ignore. There are certain files in the support config that it makes no sense to run logReduce on because they might just be full of process IDs or address spaces within the kernel, which is just like random long hex strings that really are not useful for this kind of analysis. So it ignores that kind of stuff, and there's a lot more data in there, so it takes a lot longer, but we can get some useful results. So this is just one example where it shows you here's 5 files that it's processed, and then you can click on one of those and expand it, and it will show you the actual details from that. But actually, I've got a nicer example, which is a real-world use case to show you using this approach with support configs. And conveniently, it happened that this was actually a thing that we were working on very recently, just the two of us, completely independently of this talk, something within Crowbar. And it was an issue that we found we could improve with the way that the HA subsystem works. And Dirk suggested, he found a way of improving the way it works, submitted a change, which I liked. He requested my review, although apparently I didn't like it so much that I just approved it. For some reason, I asked for some new changes. But anyway, the main thing here is that we had various CI checks passing, but this one, which is the main one, like the big CI run that spins up a whole cloud with HA configuration enabled, this failed, and so I thought, oh, well, this is a nice example. This is a nice chance to use the tool and see if it can help us. So this is the actual output. I wonder if I can do a zoom of the text. Do you think was that just risking breaking everything on the presentation? Yeah, there we go. Great. So this is the actual web page generated by the tool as output, and so these are all files within the support config. And I should mention that that this is also using a tool that I wrote called Unpack Support Config, which doesn't just unpack the tarball, but then unpacks some of the files within that, because the way support config works, it will actually combine multiple log files and other diagnostics into single text files within that. So I've written a tool that basically explodes it back out into the original fragments, so you can then see individual log files as they were on the system on which support config was run. So we can see things like under the root fs subdirectory, that's just like a mirror of the bits of the root file system on the machine it was run, where certain log files were captured. And then we can go into any of those. This is ordered by the mean distance of log lines. So using the distance, the k nearest neighbors, like the distance calculation mentioned earlier, and then looking at the mean distance across all the log lines in there. So the ones that diverge the most from the baseline that was trained appear higher on in the list. So we could look at the first one, even though this is to do with Nova, which has nothing to do with the particular component we involved in this particular pull request we were looking at. And you can see there's a whole bunch of log lines here, scoring very close to 1, 0.8. So this is basically saying all of these log lines are almost completely different to anything we've seen before in the baseline. And if you look at them, they're actually all to do with keystone authentication, which is Keystone is the sort of authentication authorization component of OpenStack. So that's hinting that maybe there's something wrong with that particular component of the cloud deployment. But we can go to, so in the particular part of the change that Dirk submitted to try and improve the HA subsystem, the most prominent log file for that subsystem is the pacemaker log. So it's a good idea to look at that one. And here you can see, so we've got, this goes back to the context thing I was saying before. So you get 3 lines of context leading up to an anomaly, and then some context after, and so on. And it's color highlighted as well. And you know how with diff, when you diff 2 things, it's split into hunks. So you might have something changed near the beginning of a file, and then nothing changes, and then right towards the end of a file there might be another change. And rather than displaying the whole file as a comparison, it just shows you those two hunks. And this is the same thing happening here, and that you can see the horizontal line separating the different hunks effectively. So yeah, if we go in there, then we can see the certain messages about this Neutron L3 HA service going wrong, and I won't go into the details of that because this is not a SUSE OpenStack Cloud HA troubleshooting talk, although I can give you one of those later if you want. But so this tells us, there's definitely something going on wrong with this service, and if we look into it, then we'll also get some hints here pointing at a keystone authentication failing. They're in here somewhere. But I mean, the details are not important. Well, there we go. There's some keystone stuff. But anyway, so at this point we could. So it's saving us. Remember, going right back to the beginning of the talk, the goal was to try and get away from doing lots of scrolling. So this is already achieving that without us having to teach anything manually to manually build a model saying, you know, any lines that have match this pattern, you know, should be treated as suspicious or failures, and any lines that match these other patterns should be treated as okay. We haven't taught it anything manually. We've just fired the inputs into the algorithm and let the machine figure it out ourselves. So, and the last thing I'll show you on here is if we go to the keystone log, which is it that one? Well, that's one of them. For some reason, these log lines are getting truncated. I guess I can search for, is that going to work? Yeah. Keystone. Here we go. And there's a bunch of keystone things that get collected. This one? Oh, next one. Oh, no, I've lost my.
I think you're slowly running out of time.
Oh, yeah. Well, so this is basically the end of the demo. There are other things that, I mean, it's, yeah, it's not, talk isn't about this particular product, but there are logs in here that will show you that effectively it was something to do with SSL being enabled and disabled, and that created problems in Keystone, which then had a knock-on failure to the Neutron L3 HA service. There's, trying to remember where it is. There's a, maybe it's web actually. Yes, here's one example. I mean, there's several log files that all point to the same problem, but you can see here that there's, you know, there's this directive, Apache directive that appears in this version that doesn't appear in the other, and I think if I remember right, this is some other stuff. So yeah, anyway, so hopefully that gives you the, I think we have to click back because we're in an iframe. Let's see. Yeah, there we go. So hopefully that gives you an idea of, like, you know, how it all works in the real world. There's other things we could apply. The context, the approach to, for example, open build service, automatic package building, that kind of thing. I'm sure you can think of other things. And I think we can finish there. We've got some backup slides relating to other stuff, but we weren't really planning to go through those anyway.
Okay, so I think we are out of time. Thanks for your attention. If you have any further questions, then catch us outside.
Thanks.